Definition of a sequence. This definition is important because we're going to use it and prove some theorems. A sequence is a function defined on positive integers. So we denote a sequence f of n using its general term x sub n. A sequence is represented by its terms x1, x2, x3, and so on. So note that this sequence or this function takes on values 1, 2, 3, 4, 5, and so on, and map them into x sub 1, x sub 2, x sub 3, x sub 4, x sub 5, and so on. Recall that we defined countable sets. So a countable set is in one-to-one correspondence with J. So we can regard each countable set as the range of a sequence with distinct terms. So let us use this note and prove the following theorem. This theorem says any infinite subset of a countable set is countable. Proof: let E be a subset of A. E is infinite and A is countable. So what is our goal? Our goal is to show that E is countable. So this is our goal. How to show that? We can find or construct a one-to-one correspondence between E and J. Well, we're going to use the fact that A is a countable set. So since A is countable, for each countable set, we can regard that as the range of a sequence with distinct elements. We can regard A as the range of a sequence like X sub n with distinct terms. Well, now I'm going to define a one-to-one correspondence this way. I'm going to say that f of k is equal to x sub n sub k. N1 is the smallest positive integer such that x n1 is a member of E. Then I'm going to take n2 and say that n2 is the smallest positive integer, which is greater than n1 at the same time. Such that x sub n sub 2 is a member of E. And I'm going to continue this process up to nk, which is the smallest positive integer such that x sub n sub k is a member of E. Since F is a one-to-one correspondence between E and J, it means that E is countable. Next definition. Now we're going to define the union and intersection of sets. Before that, let us define the family or collection of sets. So let A and omega be two sets. What we're going to do, we're going to take elements of A and connect them with subsets of omega. To each element of A, like alpha, we associate a subset E alpha of set omega. So we have A and we have omega. We take elements in A, like alpha, and we associate them to subsets of omega E sub alpha. By this representation, we can define collection or family of sets. Then the family of sets is denoted by E sub alpha. We also call them a collection of sets. So family of sets or collection of sets. Now that we have a collection of sets, we can talk about the union and intersection of these sets. The union of collection of sets, E sub alpha, alpha belongs to A, is denoted by union E sub alpha, alpha belongs to A. Note that if A is equal to J, then this union can be written as E sub 1, union E sub 2, union the rest of the members. X is in this union if X belongs to at least one of the alphas. Well, we can define the intersection between these sets. The intersection of family of sets is denoted by the intersection of E alphas. Alpha belongs to A. Again, if A and J are the same, then the intersection of E alphas, alpha belongs to J, can be written as E1 intersection E2 intersection with the rest of the members. Now we say that X is a member of an intersection if X belongs to all of the members in the collection. All of the alphas. Next theorem. This theorem says, let us have a sequence of countable sets. Let E sub n, 1, 2, 3, and so on, be a family of countable sets. Then their union is also countable. So let us start the proof. So first of all, suppose we call this set the union S. And note that each of these sets are countable. So what's the meaning of that? It means that we can arrange these using sequences. Let us arrange each set En using a sequence like X sub n times K. K starts from 1, 2, 3, and 4. And then we're going to construct an array. This. So for E sub 1, we're going to have the first row, which is X sub 1 and 1, x sub 1 and 2, x sub 1 and 3, x sub 1 and 4, and the rest of them. Our second row are elements of E sub 2. So we have x sub 2, 1, x sub 2, 2, x sub 2, 3, x sub 2, 4, the rest of them. E sub 3 construct the third row, which is x 3, 1, x sub 3, 2, x sub 3, 3, x sub 3, 4. And suppose we continue this process. E sub 4, which constructs the fourth row, we get x sub 4, 1, x sub 4, 2, x sub 4, 3, x sub 4, 4, and the rest of the numbers. So as you can see, we're constructing something similar to a matrix. We have an array. Let us write them this way. So these are all of the elements of S. X, 1 and 1. Then x 2, 1. X 1, 2. X 3, 1. X 2, 2. X 1, 3. And the rest of the numbers, these are all the elements of S. If you have repeated elements, we're going to see them here. As we constructed the elements of S, there is a subset T of positive integers that S is equivalent to T. It means that S is at most countable. So if we show that S is infinite, it means that we're done. At the same time, note that E sub 1, E sub 2, E sub 3, all of those are countable, and those are subsets of S. Since E1, E2, you can take any random subsets. Is countable. So it is infinite. And it is a subset of S. So S cannot be finite. So S is countable. And we're done with the proof.